All right, so I just want to continue on with what I was doing. I think it's pretty. I think this can get confusing very quickly. So I wanted to just take a second video to kind of go over what I just went over. So basically, I took this transfer function, which is a transfer function of s, which is significantly more complicated than what we analyzed back here, right? Back here, we had this very simple transfer function, which was 1 over 1 plus j omega rc, which you could rewrite as 1 over 1 plus src, and we did, and that's my entire transfer function, right? But now I have a new transfer function, which is this much more complicated transfer function, right? This one right here. And so to try and reason about sketching this, the way that I sketched it there is unreasonable, right? We're not going to sit here and plug in values of s, the same way that I, try and find the magnitude of this, getting it into a real and an imaginary part, breaking it down into its magnitude and phase. That's actually just unreasonable. There's a much better way that we can do it. We don't need to come over here and take the magnitude of the function and then take the phase of the function and plot it point by point. The whole reason why we got to this point was so that we could do what we're about to do, which is break the transfer function up into factors, right? These 5 factors. And the reason why this is so important is because these factors show up in the same form over and over and over again. I mean, you see these 2 factors are in the exact same form. It's 1 plus s over something, right? This one's also 1 plus s over something. And what are these 2? These are just 1 over that, right? This is 1 over 1 plus s over something. And this is also 1 over 1 plus s over something. All these transfer functions can be written in terms of these factors. The constant gain is this term here, 6. It's a constant gain term. The origin poles and zeros, we don't have any in this particular case, but an origin pole or an origin zero is basically if I were to just have a standalone s in my numerator or a standalone s in my denominator. Because that means that if I have s equals 0 or at the origin, then the whole thing goes to 0. And in the case where it's in the denominator, if I have s equals 0, then the whole thing goes to infinity at the origin, right? But in this case, we don't have any origin poles or zeros. We have simple poles and simple zeros, which take this form. These 2 are simple zeros, and these 2 are simple poles. A simple pole is just 1 over the exact same expression for a simple zero. And basically, the reason why this is so important is because these have very predictable behavior for magnitude and phase. So if we can just express our transfer function, no matter how complicated, in terms of these factors, like I said, we can just add the effects of each of the factors. We can just take 20 log of the first factor's magnitude and then 20 log of the second factor and then 20 log of the third factor, and we can add all those up. Like I said, if I had one Bode plot that looked like this, let's say that that corresponds with this term, and then I have another one that looks like this, which corresponds with this term, their overall effects get added, and this is my overall transfer function Bode plot. And so what that would look like is it would look something like h of s in dBs is equal to 20 log of the magnitude of 6 plus 20 log of the magnitude of 1 plus s over 2, right? Just like that, plus, and then we would do that for all of our terms. And we already know, I mean, we don't know, we're going to get there, but I'm going to show you now that each one of these terms has a very predictable magnitude and a very predictable phase. So as long as we can demonstrate that we can get all of this into those terms. So let me write this last one. This will be the last one. 20 log of 1 over 1 plus magnitude of 1 over 1 plus s over 6.45. Just like that. We can basically sketch each individual term on the magnitude and the phase plots. And then once we do that, we can add up their effects like I showed here, and we can end up with our final Bode plot. And we can do the same thing by if we already have the Bodhi plot given to us, we can deconstruct it in the same fashion so that we know what the poles and the zeros are in our system and decompose it back into the original transfer function of our system. Okay, so this is very powerful. I'm going to go ahead and end this video here, and from this point forward, what we're basically going to do is we're going to look at each one of these terms, and we're just going to see what the what that term's magnitude and phase look like, so that when we go to plot these transfer functions, Bodhi plots, we can predict the behavior of what it's going to look like. Okay, so I'm gonna probably go through these pretty fast in the next video because there's no reason to sit on them. You're basically going to have them at your disposal. There's a big figure or a big table in the textbook, in the Sadhguru textbook, probably in the Ulabi Maharbi's textbook as well. Let me just write it down real quick so that you know where it is. Okay, so it's page 623 of the table for these is in page 623, Sadhguru, 5th. Okay, and so it's going to show you what the phases and what the magnitudes. We're going to go over a few of them though in the next couple videos, or in the next video at least, and then we'll do some example problems so that this all kind of becomes clear. I'm sure it's still sort of confusing at this point because it's been pretty theoretical and I haven't done an example yet. But I'm going to go ahead and do some examples. I'm going to go ahead and end this video right here, and then we'll talk about these terms in the next video, and then after that we'll do some examples. All right, so I'm going to end it.